So let me start with some very simple example. We saw this in the last class, right? We said take an AND gate. We said that you invert the inputs, okay, A, B and Y. We said that this was equal to A or B. It was as if we were replacing this inverter followed by NAND gate with a single OR gate. So let us see how that lines up. Earlier we saw this with respect to the truth table. Now we will go ahead and use the laws of Boolean algebra that we just discussed and show the same is true. Okay. So for example, here this was A1, this was B1. A1 was equal to A bar, B1 was equal to B bar, and Y happens to be A1 into B1 whole bar, right? Because this is by definition of a NAND, right? And therefore you can go ahead and rewrite this as A bar, because A1 is A bar and B bar, right? But we already saw, right? We already saw that DeMorgan's laws allowed us to convert this NAND expression itself as A1 bar plus B1 bar, right? That's what we saw in the previous expression here. We saw that we were able to take X and Y whole bar and convert it to X bar plus Y bar, right? Therefore, by DeMorgan's laws, okay, I can now write this as A1 itself is A bar whole bar plus B bar whole bar or B bar whole bar. And we already saw that a double complement of a Boolean variable is the variable itself, and therefore this is equal to A plus B, right, which is nothing but the OR gate. Okay. Likewise, we also saw another example, the dual of this. Okay, A, B, Y. This happened to be A into B, A and B. That is, you take invert A, invert B, pass it through a NOR gate, you would get A and B. It's like getting an AND gate. Okay, so by definition, Y is equal to, this is A1, this is B1, right? A1 or B1 whole complement, because it's a NOR gate, right? This is nothing but, by DeMorgan's laws again, it is just A1 bar into B1 bar. Right? And this is nothing but A bar whole bar, and B bar whole bar, a double complement. And very clearly we know that double complement is the variable itself. Therefore, this is equal to A into B, which happens to be an AND gate. Okay. So therefore, the truth table is not the only way to actually simplify a Boolean expression or to find an alternate representation of that Boolean function, right? So now let's look at a slightly more complex function. Okay, I'm going to I'm going to draw a circuit using NAND gates. Okay, this is the first. So I have A, B, okay. Then I am going to combine these two again with another NAND gate, Y. Okay. So one method that I urge you to do is to actually do this via the truth table. Okay. So if I simply look at this black box here, it's essentially a 2-input gate, okay, that can take 4 input combinations 0 0 0 1 1 0 1 1, and there is just one output. So you can write out the truth table and simply propagate each combination and see what the output is. Okay, but now we are going to go ahead and focus just on the Boolean algebraic manipulation of this circuit and figure out what Y is. Okay, I am going to replace Y with just one logic gate, and you will be surprised what logic gate it is, right? How such a complex representation, reduces to something as simple as that. So let me just name these things. I am going to call this as let me call it C. Okay. So what I have here is D and E. Okay. So C itself is A and B whole complement because it's a NAND gate. Remember, everything here is a NAND gate. Okay, because it's a NAND gate. Now, what is D? D is nothing but C and A whole complement because again it's a NAND gate, right? So this one I am going to write slightly differently. I will write this as A and C. Okay, what is C? It is A and B whole bar. Okay, remember you have to be very careful about where the complement is, and so therefore write with enough space between these two variables and all that, and then I have a whole bar above that. Okay, so this internal A B whole bar is because of NAND gate N1, N2, N3, N4. Okay, so this one is because of N1. The second one, the outer one, is because of N2. Okay, so we'll first simplify this expression and figure out what D is. So it is A, and now this one we already know by DeMorgan's laws. I can write this as A bar or B bar, right? So therefore I am going to write this as A and A bar or B bar whole bar. Okay, so I will further simplify this. This happens to be, I expand this bracket here, right? I take it in. I will write this as A and A bar plus A and B bar, right? Now I am not going to simplify this any further deliberately. You will see why later. This one is 0 because and with its own complement is 0, and therefore this is simply A and B bar whole bar. Okay. So in some sense what I can do is the following. I am saying D is equal to A and B bar whole bar, or I can take a complement on both sides, right? If A equal to B, then A bar equal to B bar, right? Or X equal to Y, X bar equal to Y bar. So I am going to take complement on both sides. D bar is equal to A into B bar and B bar whole bar, a double complement, and we know the double complement reduces to the variable itself, and therefore this is equal to A into B bar. Okay, so keep this in mind. D bar is actually A and B bar whole, A and B bar. Okay. Likewise, if you look at E, it is very similar to what we did, except that B has replaced A now. Okay. So if you look at this, this is C and B whole bar. So do the same thing. It is B and A into B whole bar, right? And therefore this I will further write, and if you simplify this, you will get A bar B whole bar. Okay, I leave this as an exercise to you. Please write out the intermediate steps and show that this one reduces to A bar B whole bar, right? So this implies E bar, again by taking a double complement, it is A bar B whole bar double complement, and therefore that will vanish, it will become A bar B. So E bar is A bar into B. So now I am looking at the final gate N4. Y is simply equal to D into E, D and E whole bar. This again by DeMorgan's laws is D bar or E bar. Okay. And therefore, I already showed you previously that D bar was nothing but A and B whole bar. Likewise, E bar is A bar and B, right? D is A and B bar, D bar is A and B bar, E bar is A bar and B, and therefore this one I can just write as A B bar or A bar B. And what is this? This is nothing but an XOR gate. This is nothing but an XOR gate, a 2-input XOR gate. So what I have shown you here is just a NAND implementation of this XOR 2 gate, right? So what we have been able to do here is, without having to rely on the truth table, by using the laws of Boolean algebra, we have been able to show this for the XOR gate. Okay. So by the way, this Boolean simplification you can do for any arbitrary example. Let me pick one example from the textbook here that we can solve. Okay, I'm going to say consider f, okay, equals x bar y bar z plus x y z plus x bar y z plus x y bar into z. Okay. So first of all, in order to interpret this expression here that we have written on paper, right, we must be careful because we don't have brackets, and therefore we need to first of all understand the precedence of operators. Precedence of operators. So what we see is there are 3 operators here. Okay, one is the complement. Okay, the x bar okay. Then we have the and we have the or, right. So essentially I could, for example, alter this, right. In the previous case you also saw that some places I did use the parenthesis or brackets, okay. So that is something that you might also want to add to this. Okay, and the parenthesis, the bracket comes first. After that you evaluate the complement, then you evaluate the and finally you evaluate the or, okay. So this is the order in which you have to first of all interpret this expression, okay. This is very similar to BODMAS, brackets of division, multiplication, addition, subtraction, right. We tell you, so if you're just given an expression 4 plus 2 into 3, okay, minus 4 into or 4 plus 6, right. So you straight away know that you first have to evaluate this in the parenthesis, the brackets. This is 10, okay. Then this is going to be 3 into 2, 6, because multiplication comes, and then you have 4 plus. So you do this, it is 4 plus 10, 10 minus 10 equal to 0, okay. Likewise, when you see this expression here, so let me just take the first two terms, x bar, y bar, z plus x, y, z, right. This is not, this is not x bar, y bar, this is not equal to x bar, y bar, z plus x and yz. Okay, this is not the case. It has to be interpreted as you do x bar into y bar. So this is actually x bar, y bar, z, you evaluate and then do an OR with x, y, z. So please keep this precedence of operators in mind when you are dealing with Boolean expressions in general, okay. So let's come back to this Boolean simplification that we wanted to look at. We want to basically now find out the simplest expression here, the simplest possible Boolean representation of this expression, right. Because if you look at this, okay, if I were to go ahead and implement this in Boolean logic, I would need, so many AND gates, OR gates and so on, right, if I did not simplify this further. So therefore, we will look at how to simplify this expression by just looking at the Boolean logic, right, the Boolean expression here, right. So I'm going to first look for some patterns here that I can deal with, okay. So let me arbitrarily start off with this, okay. So I have x bar, y bar, z plus, I am going to take y and z out and then write this as x or x bar plus x, y bar into z, right. This is what I have, and therefore what I do have here now is I can reduce this x plus x bar as 1, right, and therefore I can write this as x bar, y bar, z plus yz plus x, y bar, z, okay. Now I will now further look at these two terms, okay, x bar, y bar, z plus z times, I'll take the z and out, okay, y or x, y bar. Again, I know that this can be written as y plus x into y plus y bar, the distributive law. Remember, right? We said a plus bc is equal to a plus b and a plus c, right? So therefore, and then we know this has to be 1. Therefore, this can be written as x bar y bar z plus z times x plus y. Okay. Further, I will simplify this. I'll take the z out. Okay. It is x bar y bar plus x plus y. Okay. And this I can write as, I'll keep the z outside. Okay. I'm going to focus just on this. I will say this is x plus x bar and x plus y bar or y. Again, that distributive law. I told you the distributive law will keep coming back in some form or the other, right? And therefore, I can write, I'll write this on top here, right? I will continue this expression here, z into x plus x bar. Again, this we know is 1. It is x plus y bar plus y. Okay. We know y plus y bar is 1. Therefore, this is z into x or 1. We know that x odd with any logical x odd with 1 has to give you back a 1. And therefore, this Boolean function f reduces to the literal z. Okay. So, if you had tried to implement the logic gate implementation of f in its unsimplified form, you would have basically gone ahead, okay, and used, for each of these terms you would have used a 3 input AND gate, and you would have used 1, 2, 3, 4 input OR gate in order to do the ORing of all these expressions, right? Of course, not to mention the inverters or the complement circuit that you need to get x bar, y bar, z bar and so on, right? But effectively, if you do Boolean simplification, the function f is actually, it does not even depend on x and y. So that's the key takeaway here. And this Boolean simplification allows us to do all of this without any truth table exhaustive method, right? So that's the primary advantage that we will be doing, will be exploiting going forward, where in the next lecture we will actually look at taking an arbitrary function, a Boolean function. We'll start from its truth table and then look to simplify this expression so that we can implement it in a very, very efficient manner. Thank you.